Hi everyone, and welcome back to educator.com. This lesson is on current and resistance. Our objectives are going to be to define and calculate electric current, to explain the factors and calculate the resistance of a wire, and to determine the equivalent resistance for resistors in series and in parallel. So let's start by talking about electric current. An electric circuit is a path through which current flows, and current is the amount of charge passing a point per unit time. The units of current are coulombs per second, also known as amperes, or amps, capital A. Average current is the charge passing a given point in a set amount of time. Conventional current is defined as the direction of positive current flow. This is a little non-intuitive. Typically, it's the electrons that are actually carrying the charge that are causing the current. So usually it's negative charges that are moving. Conventional current flow says that the current is going the opposite direction of the electrons. Most of the time you won't even have to worry about it, but if you're calculating currents and somebody says, well, which way are the electrons flowing? It's going to be the opposite of the direction of positive current flow. That goes back, dating back to Ben Franklin and some of the initial work done on current electricity. So, current through a resistor. A charge of 30 coulombs passes through a 24 ohm resistor in 6 seconds. Find the current through the resistor. Well, current is just delta Q over delta T. Our charge that passes is going to be 30 coulombs. That happens in 6 seconds for 5 amperes of current. How about current due to elementary charges? Charge flowing at a rate of 2.5 times 10 to the 16th elementary charges per second is equivalent to what current? Well, same formula, I equals delta Q over delta T, but now we've got to convert this into coulombs first. So that's going to be 2.5 times 10 to the 16th elementary charges per second. And if I want elementary charges to go away, one elementary charge is equal to 1.6 times 10 to the minus 19 coulombs. Units of elementary charges will cancel out, and I'll be left with a current of about 0.004 amperes, or amps. Let's take a look at charge in a light bulb. The current through a light bulb is 2 amperes. How many coulombs of electric charge pass through the light bulb in 1 minute? Well, if I is delta Q over delta T, then that implies that delta Q equals I delta T. divided by the cross-sectional area. You can almost think about it in terms of something like a water pipe. The longer a water pipe is, the more resistance to water current flow it's going to have. And the skinnier the pipe is, as it gets smaller and smaller cross-sectional area, you're going to have more and more resistance. So as A gets smaller, you have greater resistance. So if you want a very good conductor, very low resistance, you want a very wide, fat pipe that's very short. If you want a lot of resistance, you want a long, skinny, narrow pipe, or a long, skinny, narrow wire. Now, circuit elements designed to impede the flow of current are known as resistors, and resistors have some amount of resistance. It's a circuit element. The resistance of a resistor tells you how well it impedes the flow of charges. The resistance of the resistor depends upon the resistor's geometry again, as we just said, and its resistivity, that material property. So, just a picture of some resistors. Over here, we have some ceramic resistors. The color codes on them, the color bars here, tell you what the resistance is. You've got to have a decoder table that you could look up. And over here on the right, a light bulb is typically modeled as a resistor too. What you have is a wire, and then you have the resisting element up here, and then you go back down. And the circuit schematic for a resistor is going to be that. This is going to go up. That's a direct relationship, not A. As length goes up, resistance goes up. Direct, not inverse, not B. Cross-sectional area. As cross-sectional area gets bigger, resistance goes down. That's an inverse proportionality. Correct answer must be C, cross-sectional area. Now, when we talk about configurations of resistors, when you place them in a circuit, resistors can be organized in what are known as both serial and parallel arrangements. For analysis purposes, it's oftentimes useful to determine some equivalent resistance which could be used to replace a system of resistors with just one resistor that has the equivalent resistance value of whatever you had in that multiple resistor arrangement. So if we talk about resistors in series circuits have one single current path. For example, if we have current flowing to the right through these two resistors, we have one current path. That's a series circuit. The equivalent resistance for resistors wired in series is found by just adding up the individual resistances. So for this example, the equivalent resistance, R equivalent, is going to be R1 plus R2. And if we had more resistors, we'd keep adding them In this case, that's going to be 200 ohms plus 300 ohms for an equivalent resistance of 500 ohms. Just add them up. That's simple. Now for the circuit down here, we have 1, 2, 3, 4, 5 resistors. So our equivalent resistance is going to be R1 plus R2 plus R3 plus R4 plus R5, which is going to be 200 ohms plus 300 plus 100 plus 100 at R4 plus 100 R5, 6, 7, 800 ohms. So we get a total of 800 ohms in this configuration. Very easy to find the equivalent resistance of resistors in series. Let's take a look at resistors in parallel, where parallel circuits or configurations are configurations where current can take more than one path. In this case, the equivalent resistance for resistors in parallel is 1 over the equivalent resistance is 1 over R1 plus 1 over R2 plus 1 over R3 for however many resistors you happen to have. Now, it's important to note that the equivalent resistance of resistors in parallel is always going to be less than the smallest resistor in that configuration. So here we have two resistors, and if you look, if we have current flowing this way, part of the current can go that way, part can go that way. It will all recombine and then come back through here. But you have multiple current paths. It's a parallel configuration. We already know the equivalent resistance must be less than the smallest resistor here. If they're both 200, we should expect an equivalent resistance that is less than 200 ohms. How do we solve it? 1 over R equivalent is going to be 1 over R1 plus 1 over R2. Therefore, 1 over R equivalent is 1 over 200 plus 1 over 200. Or you could say 1 over R equivalent. 1 over 200 plus 1 over 200 is going to be equal to 0.01. So if 1 over R equivalent is 0.01, then that means R equivalent is going to be 1 over 0.01, which is 100 ohms, which is less than 200. So the equivalent resistance is 100 ohms. You could take these two 200 ohm resistors and replace them by one 100 ohm resistor and have the same functional resistance. Now that's a lot of work, but there's a trick. If there are only two resistors in parallel, here's a shortcut formula. R equivalent only works if you have two resistors, is R1 times R2 over R1 plus R2. So in this case, it would be 200 times 200 over 200 plus 200, which is going to give you, again, 100 ohms. This equation always works, however many resistors you have in parallel. This one is only good when you have two resistors. Let's take a look and practice some equivalent resistance analysis. Find the equivalent resistance of each of the following circuits. Well, we'll start over here with number 1. area at a constant temperature. Well, if I want to relate resistance and length, let's write a formula that shows that to me mathematically. R equals rho L over A. And I'm specifically worried about the resistance and the length. Well, as length goes up, resistance goes up. So that gets rid of number 1 and 2. And that looks like a direct linear relationship. Therefore, the correct answer here must be 3. Let's take a look at some resistors here. Which of the following resistors made of the same material has the highest resistance? Well, we'll go back to our formula. R equals rho L over A. And if they all have the same material, they all have the same resistivity. And if we want the biggest resistance, we want something that has the biggest L, so we want a very big L, and we want a very little cross-sectional area to give us a very big resistance. Which one of these has the biggest length and the smallest cross-sectional area? Obviously, the length of the silver divided by the cross-sectional area of the silver. But we know that they have the same cross-sectional area, so we can multiply both sides by the cross-sectional area. Those will cancel out. And if we're looking for the length of the copper wire, let's now rearrange this to get the length of the copper all by itself. That means that the length of our copper wire is going to be equal to the resistivity of silver times the length of the silver wire divided by the resistivity of copper. Now I can substitute in my values the resistivity of silver I get from my table. That's going to be 1.59 times 10 to the minus 8 ohm meters. The length of my silver wire is 1 meter, and the resistivity of copper from my table is 1.72 times 10 to the minus 8 ohm meters. A little bit of division and calculator work, and I come up with the length of about 0.924 meters. Very good. All right, hopefully this gets you a good start on current and resistance. Thanks for watching educator.com, and make it a great day.